Okay, welcome back. So, we will continue that discussion that we were having in the previous module. So, we looked at already in terms of definition, how the waste is defined in globally, different definition. So, now we will talk about characterizing the e-waste. As I have said in the electronic waste, in the municipal solid waste, also in the C&D waste modules, that first we need to know what is in there. So, that's then only we can think about how to manage it. So, in terms of characterizing the e-waste, let us look at the composition. What is there in electronic waste? What is really there? And I keep on saying that if you in your cell phone, you will have, if you look at the cell phone, your cell phone will have around 35, 40 elements right there, depends on what kind of model you have. So, 25 to 30, maybe 35 things are there in one cell phone. So, similarly, like in what are the things in there? Let us look at those. So, there are, if you think about any electronic equipment, there are some protective enclosures. So, there are some protective enclosures and a structural support. What are those? Those are the ones in the, like what you see, the protective enclosures you will have, and then some structural support, some plastics or metals and other, depending on what kind of equipment you are looking at. Then there is a printed wire board, which is the important stuff. So, it is a printed wire board which has all those chips and other things in there. Then you have a display device, there is a memory device. Like for our laptops and desktops, we have those RAM and also our hard disk. Then we have some motors, compressors, transformers, capacitors, those things are there. There could be some lightning device, which batteries, wires and cables. So, in general, these are the different components which is there in electronics. If you take an electronic waste or electronic product, you take it apart, put the different components, you will find these are the ones which shows up there. And what proportion, that depends on type of some type of instrument that we are looking at. Some the composition percentage wise will change, but these are the different components that you will potentially see if you take any of these electronics. So, for example, if you go to cellular phone, here you have around 8.4% is metal. We have lots of plastics in cellular phone, and plastics are actually going up, metals are coming down. Then we have printed wire board, which is around nearly 40%. We have display unit is 4%, and there are some miscellaneous parts which is there as well. So, overall, as you can see, we have like a cellular phone means a good amount of plastic, and there is a then we also have printed wire board. So, that's printed wire board will have different types of heavy metals and other things present there. So, that's, and then more as we make progress, we are actually reducing the metals, we are using more and more plastics. If you go to computer monitors, again we have display unit, LCD, CRT, like the glass is very high, and then we have some ferrous, some non-ferrous, some plastics, printed wire board, wires, those things are there in computer monitor. Color television, again you have some ferrous metals, non-ferrous metals, some plastics, printed wire board. Display unit is the major one. Then you have printed wire board, which is it's around 10%. Wires, lots of plastics, around 22%. So, say if we can replace all this, say if you think about these kind of pie charts, those ferrous plastics, if we can take those plastics out, that can go to a plastic recycler. That's what we can think, and at some point, at some places probably it can. But the problem comes because these plastics that is used in electronics, they are not either like usually when we talk about plastic, we have these numbers, isn't it? PET, HDPE, PET is number 1, PET resin, that's the resin code as well, 1, 2, 3, 4, 5, 6, 7. So, the problem is in the stuff kind of plastic that is used in electronic industry is the blended plastic. It's not just one, either it's not PET, HDPE, many times there could be at some point they are used as it is, but most of the time it's kind of a blended plastic, and the blended plastic it's very difficult to separate. So, it may not be a good recycling, it may be more, it's maybe a good candidate for incineration rather than the recycling. So, those things are so up there. Then the flat panel display, as you can see the flat panel, the display unit has gone down, the percentage for display units has gone down. We have some wires, the highest that we see is the plastics again here over here, and metals. Now, ferrous metals we saw that so quite a bit, and ferrous again is coming down as well. So, those things are there. Then in terms of the plastic, as I was saying, there is a kind of a mixture of you have acryl, nitrile, butadiene, styrene, ABS, high impact polystyrene, polyvinyl chloride, polycarbonate, polyethylene, and the blends of above. So all these common polymers are there where we use lots of mixtures of those different types of plastics which is out there. So and then there are lots of trace components. So there are some inorganic chemicals which is lead, mercury, cadmium, beryllium, arsenic, silver. So those are the inorganic chemicals are there. Then we have some organic chemicals in terms of the PCBs and flame retardants. So those are the organics part. So we have both inorganic as well as the organic which is present, and many of these, for example, lead, mercury, cadmium, beryllium, arsenic, all these have certain toxicity. They are listed as certain adverse environmental and human health impact. And similarly, PCBs are known as have some sort of negative impact as well, and the flame retardants are known for their negative impact. It's been in news in recent years for like environmental and human health impact. So there is a toxicity concern. So this is your periodic table. I have been talking about periodic table for so long, and I thought now we are coming to the end of the periodic course. Why don't I show you this periodic table? At least you will remember. This is what you have already all of you have seen it, and so anything on this periodic table cannot be created, cannot be destroyed. I have said that many times. So we can change its forms. So what are the toxicity concerns from the e-waste perspective? So lead is we are concerned about lead. It's the printed wire board, mostly CRTs. So lead, why we are concerned about lead, which I have explained earlier as well. Lead it does affect the brain development. It's a neurotoxin basically. It affects the brain development, especially of small babies. The brain does not develop very well if they get exposed to lead. So that's why in many countries in the world, they actually, as soon as the baby is born, they look at the blood lead level of the baby, and then if it has high lead level, they try to treat it so that baby has a proper growth. So, this is lead is one of the major concern. That's actually the number one concern which caused a lot of e-waste issue around the world. Like a lot of e-waste media coverage around the world was because of the lead, because lead showing up. Because of lead, it was becoming a hazardous waste. So, where is the lead? If you look at the old color CRT, the funnel has 24%. Neck has 30%, frit has nearly 70%. So that's what the old color CRTs that you see it here, and monochrome CRTs. When you look at the monochrome, it's a neck around 30%, funnel is 4%, face is around 3%. And when we say 4%, 3%, these are actually percent by weight of that particular. It's not the percentage of lead there. It's not the total. That's why the total doesn't add up to 100. Or maybe it's more than 100. If you add up all this thing here, actually it will come out to be more than 100. But what we are talking about, that funnel is 24% lead, means the out of the weight of the funnel, 24% is lead. A neck, out of the weight of the neck, 30% is lead. Out of the weight of the frit, 70% is the lead. So that's what it is trying to tell you there. So then there are metals in solder, different types of solder. Tin lead solder was very famous, it was used a lot. Now we are for last several years we have been phasing out tin lead solders and try to use other solders. So tin lead was the most common. Then tin copper, tin silver copper, bismuth tin silver, bismuth copper. So there are a lot of different combinations are out there which people are trying in terms of different types of solder for electrical electronic purposes. So another is your arsenic, which is a toxicity concern, antimony, cadmium, mercury, beryllium, and so these are some examples of the concern. And this is arsenic is used as a semiconductor, antimony is used in solder and CRT glass. Cadmium, it's a used for contacts and switches, plastics and batteries. Mercury, we have again lighting, switching and relays. Beryllium, CPU, motherboard, heat sink. So those are the ones where we use these elements. So we need to use those elements anyway. So and then it's a resource. So toxicity is a concern, and at the same time it's a resource. So why should we just throw it away? Why don't we try to recover material from out of that? So in terms of the resource, if you look at copper is around $4 per pound. So $4, say even for our calculation sake, let's take 60 rupees as a dollar. So it's around 240 rupees per pound. So it's if you multiply it by, so it's around 500 rupees a kg, something around that. Yeah. So that's so, and then silver. We have silver, we have gold, we have platinum, palladium, rhodium, and as you can see their prices, they're pretty expensive stuff. So if you go and try to buy this stuff from the market, they're pretty expensive. So the question is, why can't we recover? And these are there in the electronic waste. They are not there in a great quantity, they are there in a fraction, they are there in the trace amounts, but that's why it is difficult to take out them as well. But say if we can recover these elements from this periodic table in a environmentally safe, in human health safe manner, and at the same time not polluting the environment, and using the technologies which might be out there. So if we can use this and then recover these elements out of those waste stream, it will really help in terms of our as a resource. So as you can see, these are not cheap stuff. These are expensive stuff. And as you can, copper, then silver, gold of course. Lot of even there has been many times we hear that there is a lot of gold in US that probably will be enough for the country. I'm not sure whether that's true, but at least there is a substantial amount of gold is there. Several researchers, several papers have been published trying to project how much gold is there. And in Japan and some other countries, they are recovering gold. In India also, people are recovering gold from this electronic waste, but it is being mostly done in an informal sector, and where they use all sorts of crude methods to get that little bit of gold and little bit of copper. Organic chemical, PCBs, brominated flame retardants, those things are there. PCBs are, let's say, potential carcinogen. Brominated flame retardant also has like a human health impact. And again, some pictures of different types of wires, different types of like the desktop and all that. Typical BFR of concern is PBDEs, which is the polybrominated diphenyl ether, which is then you have the hexabromo chlordodecane, then you have C-decabd, then you have tetrabromo bisphenol A, so TBBPPA. So there are different types of BFR, brominated flame retardants, which is used in terms of its application for electronic industry. So the thing is that we need to find out which one of them is like what is the environmental impact from these, what is the human health impact from these, so that we can manage them in a proper way. So so that's in terms of what are the different elements present there. But in terms of now the estimate, the composition estimate for personal computer and CRT monitors, as we can see over here, so there is some lead, there is a glass, TBBPA, plastic, PPO, and HIPS plastic, ABS plastic, aluminum, zinc, copper, steel. So as you break it down further, you see that there are lots of different components which is there. Most of it could be potentially recycled. Some of this which could not be recycled or recovered has to go to a landfill, and based on what is the waste characterization, we can decide whether it will go to a hazardous waste landfill or a regular landfill. So in terms of so that's in terms of like a composition. And then we have to look at the generation. So first of all, how much so what we are doing so far, we started with defining the e-waste as per the European Union definition and some other definition. Then we also talked about this one, we talked about in terms of what are the different components, what are the steps in terms of the e-waste management, and then we start looking at in terms of what are the composition, what is in there, what kind of toxicity they have, if it's a resource lost, what kind of resource we are looking at in terms of the loss of the resource. And then after that we are trying to see in terms of like organic chemicals, brominated flame retardants and other stuff, in terms of how these are is being if it's there in the environment, if it does come out from electronic waste and impacts on human health and environment, what are the different components which is there which will have a negative impact. So and there we also had, if you look at this particular pie chart, we also saw what are the, like now it's a more detailed pie chart. We are looking at the individual components. Most of these components can be potentially recycled, but some of this component has to go to the landfill. So being said that, so this is kind of in general about e-waste. Now we want to know in terms of quantity, how much e-waste is actually being produced, not only in India but around the globe. How much e-waste is actually being produced? And several authors have projected historical, current and future generation, and it says that generation represents approximately 1% of total MSW. Let's say old one, they found that around 1% of total MSW waste is e-waste. Now that number will be much higher. Similarly, in European Union also they were trying to look at e-waste, that they found that in European Union they produce a little bit less than US, but they still produce substantial amount of e-waste. So in general, and then there was a study done earlier where they found that if you look, current MSW in the US is approximately 250 million tons. So based on that, what is the electronic waste being produced? So electronics in waste approach, where they looked at how much waste is, this is the MSW figure in terms of how the MSW is being produced. So out of that MSW, the electronics are also coming up. In terms of electronics, we didn't see much of cell phone coming out until 2010, but there were computer components and television components was much higher. And the computer components actually took over the cell. Earlier it used to be the television computer which used to be higher. For most part it was kind of going back and forth, but after that would be year of 99, 2000, we had a cell phone, like the computer components. The computer basically took over the television, so the computer components becomes much higher. And if you do it like now or a few years down the line, you will see actually the cell phone components now is the leading one, because lots of people are using those cell phones. So here are some of the individual end of life estimates between 1982 and 2010. So in terms of desktops, portable hard copy drive, mice and keyboard, CRTs, flat screen, TVs, projection, monochrome, TV flat screen, cell phones. So as you can see, the cell phone is almost towards the bottom. We see cell phone is actually right at the bottom, those gray line that you see over there. And then on top is the toppest one actually is, I think, is the PC CRTs. And then there was a drop in PC CRTs after 2005, 2006. And the reason for that is the old TVs or old computers used to have those CRTs. Now from early 2000s, we have started going away from CRTs, started using those flat screens. So flat screens has started coming in, so CRT was gone. So as the CRT was gone, so you start seeing less and less of them showing up in the waste stream, because people are not buying CRTs for almost 10 years now, more than 10 years. So you will not see those CRTs showing up in the waste stream. So that's kind of gives you some idea. So as you can see, for the different types of categories, again you have different for different types of waste category, waste stream, you have different amount in terms of waste generation rate. Okay. So in terms of the management, either it will go to landfill or waste to energy, can be recycled, can be returned to the owner or manufacturer. So this is how it's discarded by the generator. These are the ways it is kind of managed. So estimation on recycling and disposal, if you look at the distribution of end of life products, out of total end of life, which is the blue line. So this is the total blue line and this is a kind of a US figure, or the globe. I think that this is a US figure. So it's this is the blue line of your distribution total end of life products. So the green is the total disposed. So green is the one which kind of shows the total, whatever is there, most of it was disposed. And so total recycled is what we see at the bottom over here. So recycling is very, very low. So what is this graph is, the message I want to convey from this graph is, we have been producing a lot of end of life products from electronic waste, and end of life product from electronic waste is keep on increasing. Again, these are in tons. So one thing we need to understand is, since they are in ton, earlier the e-waste used to have more and more ferrous, things used to be heavy. So when we go to the lighter version now, things are becoming lighter, your cell phones are becoming lighter, so everything is becoming lighter. So if it becomes lighter, those the numbers will get affected over here too. So in the waste stream, in your million tons, you may have more item now, but total weight will be less. That's the impact of where you have change in the product, the way the product is made and the way the product composition is. Since more and more plastics are being used, also although more and more electronic might be coming in. So with this graph, as you can see, you see that the slope is not that high in terms of production, but we cannot be sure in terms of production. Maybe the quantity is going up in case of production of e-waste. So in case of discarded e-waste products, their value is, the volume of that is going up, but since they are lighter products, when you look at the weight of them, it may be still the same or maybe a little bit lower. So that's why the slope, you see a very gentle slope rather than a steep slope, as you would probably expect from electronic waste, the way the things are produced. So as you can see, the recycle part was very low, which is in fact just less than, if you look at just less than 500, so maybe around 400, and then if you look at around the total, it's more than 2000. So less than 20% actually is getting recycled. So that's kind of same, and that's where we need to kind of move and do stuff. So in terms of management, once it's discarded by the generator, it can go to landfill, can recycle, can return to OEM. But the major driver is recycling required? Is the recycling mandated? If the recycling is mandated, then probably people will do that. Is e-waste a hazardous waste? That's another thing. Is the e-waste that we have is a hazardous waste? If it's a hazardous waste, again, people will try to, it has to be managed as a hazardous waste. So, but as I said, as per definition of rules, e-waste is exempted from the definition of hazardous waste. So hazardous waste determination, you saw this slide earlier probably, that we try to do it's not explicitly listed as a hazardous waste. He said e-waste is not explicitly listed as hazardous waste. It could be hazardous as a result of the toxicity characteristic. So toxicity characteristics is determined using TCLP test. So that's the TC is determined using the TCLP test. So you do the TCLP test and you compare that to the standard. So this is just some example standards shown here in arsenic, barium, cadmium, chromium, lead, mercury, and all that. So you can use you can do that, and then you can at the same time you can compare with the standard. So that's a TCLP test. So in terms of the RECRA 8, so we did a lot of testing, and then we found that lead was the only element which is likely to cause e-waste to be ATC hazardous. So lead was showing up when we do the TCLP test, and the thing is for lead is lead does show up a lot with the presence of acetic acid, because of acetate ion and the lead ion, they really like each other, and then they come together, and that's a lead does leachability shows up. So there has been some research done where in our lab as well, we found that lead is the only element that is causing e-waste to be TC hazardous, but other things also do leach out. Then there is a California 16. So if you are, California has an additional testing for hazardous waste determination. So under this requirement, e-waste may be hazardous for lead and copper. So you need to better check whether it's there or not. So in case you have been asked to do that. So lead and copper is what they found it to be maybe hazardous for lead as well as for the copper. So in terms of TCLP test, again, as I have mentioned this earlier, you take your solid waste, size reduced to less than 1 centimeter, leach 100 grams for 18 hours at 30 RPM, filter the solid, analyze the leachate, and then you get your numbers. And then you take this number and compare with the previous slide, that you compare with this data over here. So you take those X value that is there in that particular slide, and then you compare, and then you compare that with these numbers. And if it exceeds any of these numbers, it becomes a hazardous waste. So that's how we have talked about TCLP test earlier. So Okay, so what is the what is the chance of in terms of the TCLP test, how to do it on e-waste? So as if you remember from this previous slide, we have to get this a size reduced sample. Sorry. So we have to do it as a size reduced sample. So to do the size reduced sample, you have to get a like a basically why it's to get a representative sample to make the reaction go faster. To have a representative sample for electronic waste, we need to get a representative sample. So how in the world you think that you will, from this kind of stuff, you will kind of get a representative sample? So there are different items in there. Say we already talked about that the thing of concern is on the thing of concern is the our like a printed wire board and things containing heavy metals and organics. So not entire electronic waste is has hazardous nature. The casings, the glass in the front may have some lead little bit, but we don't know. But those so those casing and other stuff, some of those wires and other things too, they are not have any adverse environmental impact when it is disposed. It is that heavy metals and the organics which will create a problem. So how to get a representative sample from this waste pile to do a TCLP test? It's challenging, isn't it? So how to get 100 grams? So should I just take 100 grams from one particular aspect here? Or if I'm doing a like a computer or a monitor, this is a monitor, or a copier, this is a copier machine I think. So like a printer machine. So should I just take the plastic casing and get that 100 gram, or what should I take it? So the answer to that is you should try to take the different components in the proportion that they come into the instrument, into that particular waste. Say you have to take, say if there is a plastic, there is a glass, there is a metal, and there are some other components. So you look at, as per the weight of that machine, what are the weight of the individual category, whether it's a plastic, glass and other stuff. So based on that you take, so if it's a plastic is 10%, so out of 100 grams you take 10 grams of plastic. Printed wire board is 30%, so you take 30 grams of plastic. So that's how you kind of, so 30 grams of the stuff which has printed wire board. So printed wire board, so that's how you come up with a representative sample. So, and the other thing is to size reduce, like how will you do the size reduction? That's again a problematic how to do that. So one option is to cut and by hand. So if you have a cheap labor available, you can get this, let the people cut in. It does require some effort. You cannot do much in a day, but you can size reduce it by hand, and then that takes the sample and do the TCLP. Other option is to grind it, where you can grind the sample and put it through a grinder, and then you get this kind of sample after the grinding, and then you are given further size reduce it. So you can further size reduce it to do the TCLP test. So then what is the another option we have? Another option is you lease the whole thing. Why to even get the 100 gram sample? Because many times in the electronic industry, or when you talk to people working in the waste management field with electronic waste, they said when we put it in a landfill, it's not going to broken down to less than a centimeter. It's going to just stay as it is. Probably the compactor will come, it may just crush it a little bit. So why don't, the other thought was, why don't we just take this whole thing and make a big drum and dump it the whole thing there. Based on the weight of the instrument, we will have 1:20 liquid to solid ratio, so multiply it by 20 to get a like a liquid there, and let's let it rotate. So but to get a big drum rotator, that's what we need for doing this if we want to do the leaching of the whole thing. So we had a chance to get this drum rotator made, which was used to do this TCLP test in a big container, so that really it's again has the same rotation as required for TCLP, so same revolutions per minute. And we also tested out some samples where we did TCLP on this drum rotator as well as on regular TCLP rotator, and the data was more or less kind of in the similar ballpark. So that's we decided that we can probably use that, and we reduce the RPM as well. We rather than using 32 RPM, we reduce it to around 23 or 24 RPM, if I remember correctly, and that also worked out to be okay. So those are stuff in terms of the extractor, modification of the extractor to get a representative sample. So how you do that? You disassemble your electronics, then you put it on large scale modified TCLP rotator. That's how it's getting rotated. Then once you have the large scale, you can have a data from different types of data on different types of electronics. So all the different types of electronics were tested, which I will share that will take some time. So we are coming towards the end of this video, so I'll stop at this point in terms of the lecture, and then in the next video we'll talk about what are the results that came out, and I will kind of maybe back up a few slides to recap some of this stuff. But in terms of the large scale TCLP test is done to find out whether the solid waste is a hazardous waste or not. So for things like electronic waste, where it's very difficult to get a 100-gram sample, the thought process is, why don't we do it in a large scale? So when we do it the large scale, it's a big drum. To rotating that at 30 plus 30 RPM was difficult. So we reduce the RPM and to make it go a little bit of and then we tested it, whether there is an RPM effect, whether there is a rotation change in revolution impact. All those things were tested as part of a master's thesis, which is already published out there. So let's stop here. Again, do that small survey on e-waste like you did for municipal solid waste. Please do that. It will really be helpful to all of us because we'll like to see how the e-waste is being managed in the country as of now, and we'll share that information with you towards the end of this particular course. So with that, let's stop this video, and then I'll see you again in the next video. Thank you.